Well, hi everyone. Can everybody hear me, by the way? Can just someone say yes or something? Raise your hand that I can see that you can hear me. No one
Yes.
say. Yeah, you can hear me.
Yes.
Okay, all right. Hi. So, welcome back. Nice to see you, everyone. Hang on, let me get the list of so I can see the people here. There you go. Now I can see the people. List of people. Okay, all right. So, what's on the agenda today? So, what we're doing today, to remind you, we're going to be continuing our Jaynes-Cummings model. So, one, I'm going to give you a quick recap of what we did last time. Remember, we started discussing the Rabi model. We moved on to doing rotating wave and Jaynes-Cummings. I'll give you a quick recap of that. And we looked on resonance. So we had our two-level system, our atom. It was on resonance with our single electromagnetic mode. We were thinking about a cavity. Okay, we're thinking about a cavity because that's also the next system that we'll see experimentally, cavity QED. And so I'll do a quick recap of that. And after I do a quick recap of that, we're going to move on to the off-resonant regime, or what is called the dispersive regime. And when we're done, so first we're going to do a recap of JC model on resonance. Afterwards, we're going to move to the dispersive regime. And after the dispersive regime, we're basically going to be done with this atom cavity Jaynes-Cummings model. And then we're going to be moving into our next phase of the course, so we're going to be shifting gears, and we're going to be looking at the more advanced technologies. We're going to start with cavity QED, which is not a platform for quantum computing per se, but you can do nice things with it. It is probably the nicest system to explain the Jaynes-Cummings model on. Okay, as I told you in the intro lecture, the person doing most of the demonstrations in that system was Serge Haroche, and really he got the Nobel Prize for showing how the Jaynes-Cummings model comes into play in that system. So we're going to be looking at that system. I will explain how that system works. And then we're going to be looking at experiments that were done in that system and how features of the Jaynes-Cummings model come into play, both on resonance and in the dispersive regime. Okay, so that's our plan for today. So that, and I'll do this for, so we're going to be talking about circuit QED. We're going to be looking at that system. After circuit QED next week, maybe we have to tie some things up with circuit QED, but once we're done with that, we will move on to sorry, not circuit QED. I meant cavity QED. Sorry. Cavity QED. Yeah, someone should have corrected me. Anyway, after cavity QED, we will move on to circuit QED, which is basically superconducting qubits. I will be giving those guest lectures, about that platform. And we'll see also there how the Jaynes-Cummings model and all these models come into play. And we'll also specifically see how that moves us forward towards building a quantum computing platform. So we'll see how that emerges in that platform. And that will take us 2 weeks. And then on January 17th, you will have the guest lecture by Roy Ozeri. He's the vice president in Weizmann, and he does trapped ions. So he's going to give you the guest lecture on that. And a week after that, that will be the last week of the semester, you will have the guest lecture by Yoav Sagi. He's from the physics department here. He does cold fermions, and he's going to explain to you about neutral atoms and how that platform comes into play in terms of quantum information as a platform for quantum computation. So that's kind of like the general plan of where we're going. What I skipped out here, number 3, is after I finish doing this, we'll take a short break and we're going to be discussing your seminars. Okay, so what is the requirement for the seminars? What is expected for you to present? What is the format? And so on and so on. So you can start thinking about those. Okay, so that's the plan for today. Any questions about the plan for today or the continuation? No. Okay. All right. Great. So let's start with with a recap of what we did last time. And last time we did the Rabi model. So we took a model of a two-level system coupled to a single harmonic oscillator mode, single cavity. So we imagined a cavity, and we have some kind of mode, and we have inside this cavity just a dipole, and it's sitting there. Okay? And so the Hamiltonian that described the Rabi model was h bar omega q over 2 sigma z. This was the part of our two-level system, our qubit. Then we had h bar omega a dagger a. This was our harmonic oscillator. And then we had our interaction term, which was d. That was the dipole term, epsilon q sigma minus plus epsilon q sigma plus dot, I think we had an I because it's with the minus, it doesn't matter, I epsilon naught epsilon c a minus epsilon c star a dagger. And this was the interaction term. This was the electric field, which we saw before, the quantized electric field. And this was our dipole. And then what we did is we had a long discussion about the rotating wave approximation, where it applies, where it doesn't apply. What we saw basically is that the Rabi frequency, which is proportional to d times epsilon naught, the Rabi frequency has to be small with respect to, this was omega c, I think, right? Omega c and omega q, and also omega c minus omega q had to be small with respect to omega c plus omega q. And then we could drop the fast rotating terms. Okay, and this was what we discussed last time. And under this rotating wave approximation, this interaction part turned into the following thing: h bar omega naught over 2. There was a minus here. A sigma plus minus a dagger sigma minus. And this is what we call the JC, Jaynes-Cummings model. So this is what we did last time. And we discussed this term. And what we saw last time is that this term on resonance basically was a swapping of excitations at a certain frequency. Okay, so on resonance, we saw that basically the energy levels they were split, if you remember, into doublets. And the action of this this interaction term was to conserve the number of excitations. So if you were in a certain doublet, you would stay and you would have these oscillations in the doublet, and the frequency of the oscillations were the nth Rabi frequency, if you remember. So close to resonance, if you look at delta, which we defined as omega c minus omega q, we had this, so this was the energy, and we had these two steady states. This was plus, and we called this minus. And this was true for each n. So for each n, we had plus and minus, and the splitting here, which is basically how fast, depending on the basis that we're looking at, okay, but the splitting here is how fast the two states in the uncoupled bases are swapping excitation. And we saw that omega n was just omega naught square root of n plus 1. And these were the steady states, and we also saw that in the uncoupled bases, we looked at the dynamics, and this is basically the swapping. So this is a solution for, if we start, I gave the example solution, if we start psi naught equals E and some n, then E goes to G, and n goes to n plus 1, and then you have the following dynamics, which is just cosine omega n over 2t En plus sine omega n over 2 t g n plus 1. And these were basically the Rabi oscillations in that doublet, which oscillate at the frequency omega n. And if we look just at this spectra over here, so for that specific doublet, it basically just behaves like a two-level system. Okay, a two-level system in a classical field within this submanifold, if you want. Okay, so with respect to that, sorry, my throat is drying up. So with respect to that, are there any questions on resonance? What's happening? Yes.
In the James Cumming model, shouldn't it be a plus between the A sigma plus and A dagger sigma minus?
You can have a plus, but then you can remove that and then there.
So these two are equivalent Hamiltonians?
Yeah, it's the same thing. It's just a matter, it needs to be Hermitian, right? So if you have the I out here, then you need a minus. And if you don't have the I, then it's just a plus. But the dynamics are identical. You can absorb the I into the phase of the Rabi frequency if you want. Okay.
Okay. Thanks.
Yeah, I think you might be right that it might be more common to write it this way, but you see them both ways. And I think I might have interchangeably written it one way or the other, here and there. Any other questions? Okay, so we can move on to the dispersive regime. Okay, so in the dispersive regime, what we are assuming is that we have a large detuning. Detuning is 1n, I think. Such that delta, which we defined as omega c minus omega q, is much larger than the vacuum Rabi frequency. And this is what we call the dispersive limit. And what we're going to do in this limit is what we do every time in physics when we have a large parameter and a small parameter. What do? Anyone?
Neglect. Perturbation theory.
Okay, thank you. Perturbation theory, exactly. So basically what we're going to do is perturbation theory. I mean, in physics, we don't know how to do many things. We only have, you know, a finite set of things we know how to do. If the problem fits with the finite things we know how to do, we do them. If we don't, we go look for a problem which can use one of those finite set of tools that we know how to use. Okay? To that, there is an exception. There are smart people who try to develop tools which the rest of us then later use. Yeah. Okay. So, perturbation theory. So we're going to do perturbation theory in the parameter omega naught over delta. And this essentially is going to diagonalize our Hamiltonian. Okay, remember our Hamiltonian is A dagger sigma minus plus A sigma plus. So these are off-diagonal terms. And what we're going to have after the perturbation theory is we're going to just have diagonal terms in our Hamiltonian. So we're going to take, so our Hamiltonian is going to have two parts. One part, H naught, this is the diagonal part. So this is H bar omega C A dagger A plus H bar omega Q over 2 sigma Z. So that's, I'm going to do like that. That's H naught plus V. And V is going to be just H bar omega naught over 2 A sigma plus A dagger. The plus and the minus can be like that. Sometimes the plus on the sigma plus and sigma minus, sometimes it's up, sometimes it's down. And I confuse you with that, and I apologize. So if I confuse you with that, just correct me and say, oh, you put it up instead of down or whatever. But in books, you will see it interchangeably used up here and here. It doesn't matter. It's the same thing. So this is our off-diagonal term. So this is going to be V. And to do the perturbation theory, what we're going to do is we're going to look for a transformation. So we're going to transform using U. We're going to look for some transformation U. That is e to the I eta. And this eta here is going to be time. So this is going to be time independent. Okay, so I'm going to show you a very general thing now, okay, for such a Hamiltonian. So we're going to have U time independent, and basically we're going to look for the right eta, the right transformation, that will cancel out this term and give us the right series. And we're going to do this basically using BCH, Baker-Campbell-Hausdorff formula. And if we use BCH, we can calculate the transformation. So a general transformation, if you remember, is just U, H, U dagger, plus, or sorry, minus, what plus, minus, I, U, U dot. But because this is going to be time independent, then this term is going to drop due to the fact that it's time independent. And then we're going to be left with H plus eta H plus half eta, the commutator of eta and H, plus more and more terms. So this here, I used BCH to just write this thing. I'll try to fit another line here, maybe, to help. You know what? I'm going to write this line here on the new board. I'll move to a new board and rewrite that line. Okay, so over there we had HU dagger plus the time-dependent term which we threw away, and this was H plus eta H plus half eta H plus so on and so on. Now I'm going to plug in H equals H naught plus V. Now remember, V is going to be our small term because V is proportional to omega naught. Okay? So we're assuming that V is a perturbation. This is why we split it up this way. But we're not using that fact yet. Okay? So what we have is we have H naught plus V. This is this term over here. Just rewrote it. Now we're going to have eta H naught plus eta V. All I did is write the next term. That's these two over here. Plus we're going to have half eta H naught plus more and more terms. Okay, where I threw away the term with a V over here already. And now comes the part where we get to choose what eta is. Okay? And we're going to be choosing eta, so we choose eta in such a way that these two terms here, V and this thing, cancel out. And then we're going to be left with this term up here only. Okay?
Shay?
Yeah?
Can you explain why you didn't consider the terms with the eta and the V in the second term?
Well, they're going to be smaller because we're assuming that V is a perturbation. Okay, so it's going to be smaller. You're going to see how it comes out. I mean, you can keep those terms and then justify it later. Okay?
Thank you.
But basically, because each term, once we choose eta, it will become more apparent. Okay, but you'll see we're going to have omega naught over delta. And as the terms go further and further, you're going to see that they're going to be smaller and smaller in this series. Okay? So what we're doing here, we're going to be choosing eta such that, well, let me write eta and then I'll show you what comes out. So we're going to choose eta to be omega naught over 2 delta. So delta is omega c minus omega q, which is large. But remember, not too large because we're still within the rotating wave approximation. So we're still within that. So it's large, but not too large. Times a sigma plus minus a dagger sigma minus. And we chose it this way because we want, if you calculate the commutator of eta and H naught, you will see that it comes out to be minus V. So these two terms are now going to cancel out. And then if these two terms cancel out, then our new H, our transformed H, is going to be H naught plus half eta V. The half eta V comes from the fact that here we have eta V, the commutator, but eta H naught, this gives us minus V. So we have minus half eta V plus eta V. That leaves us with half eta V over here. So we're left with that. And if we do the calculation, then we're left with H bar omega C A dagger A plus let me write. So I'm gonna put a tilde over here. Maybe I don't need this. I'm gonna put a tilde over here, and I'll explain in just a moment what is this tilde. Plus H bar omega Q tilde. It's a renormalized energy, so it's a value which is slightly different than the original value that we had. Plus H bar chi, and I'll define chi in just a second, over 2. A dagger A sigma Z. So this term here, this is the new interaction term. This is the important term, where chi is omega naught squared over 2 delta. Okay, so this is our small parameter, chi. And now note that our interaction term is diagonal in the bases. We have A dagger A and sigma Z. That's our, basically, our number operator, so-called number operator for the qubit and the number operator for the field. So we're commuting with that. This omega C here is very close to omega C. If you do the calculation and you plug in and you do the commutators, you're going to get extra terms, and some of these terms are going to have A dagger A in them, and some of those terms are going to have sigma Z. So you just take them and absorb them and change the parameter over here, which slightly renormalizes these numbers, and then omega C is basically going to normalize roughly like omega C minus chi over 2, and omega Q is going to renormalize roughly like omega Q plus chi over 2. So there's a slight shift of the energy of the harmonic oscillator and a slight shift of the energy of the atom. Now, the slight shift, to some of you, the slight shift of the energy of the atom might be familiar, and it's called, anyone know what it's called? Give you a clue? Meh, meh. No? No one? Lamb shift? So this is a kind of manifestation of the Lamb shift. When you have an atom and it's in free space, and if you do a light matter interaction course or some QED course, you will do this in a rigorous manner, but the frequency of the atom, the transition energy of the atom gets shifted a little bit due to the interaction of the vacuum fluctuations, okay, with the electromagnetic mode. And this is basically the single mode manifestation of this thing. But the underlying behavior is that the vacuum fluctuations are basically pushing you can think of it as them pushing away the electromagnetic field and the atom from each other. Okay, so this is kind of a manifestation of this Lamb shift thing. Okay, so this is our dispersive Hamiltonian. This is what is called the dispersive Hamiltonian. And now I'm going to get to the next board, and we're going to discuss what this Hamiltonian looks like. now. So we're going to discuss the spectra and what the energy levels look like. Okay? If you remember, on resonance, so this is the board on resonance. On resonance, we were split up into doublets, and each doublet was split by omega naught. Okay? And what I'm going to do now is I'm going to do the energy spectrum for our dispersive Hamiltonian. Okay, so the dispersive Hamiltonian, I'll just rewrite it over here. We have h bar omega c a dagger a plus h bar omega q over 2 sigma z plus h bar chi over 2 a dagger a sigma z. So let's see what this looks like. So if we write the energy level diagram, so we'll have some level, this is going to be 0 G, so 0 photons in the cavity in G. Then above it over here, this is E. We're going to have 1 photon in the cavity in G, 2 photons in the cavity in G, and purple, this is going to be uncoupled. Okay, so we're looking, so in purple I'm drawing just the bare levels, and then I will show you the shifted levels. Okay, so the bare levels like this, so we're going to have 3, this is G, and the energy difference over here is just h bar omega c. Okay. And now let's write the energy levels for. I'll try to make it equidistant, but I'm sure I'm not doing it justice. This will be 0 in E, 1 E, and 2 E, where this just h bar omega q. Okay, so this is the difference between G and E with 0 photons, and this is the ladder for each harmonic oscillator. So this is the harmonic oscillator ladder over here. And what happens due to the interaction is that the levels slightly get shifted. Okay, remember delta, this is delta. Okay, delta is omega q minus omega c. And what happens is you have a little shift over here. And something like this. And then you have a little shift. This goes up and this goes even further up. So you can think of it a little bit as the atom, okay, the two-level system, and the field are basically repelling each other a little bit, and there is some small interaction. This is the interaction term. I will elaborate on it in just a second here. And this interaction term basically shifts the frequency dependent upon the excitation of the qubit and the number of photons in the cavity. Okay. A nice way to look at it is if we look at the spectrum. Okay, so let's look at the spectrum. This is So what I want us to do now is to look at the spectra of this Hamiltonian. Okay, the allowed transitions that we have in this Hamiltonian. So what I'm going to draw now, and I think this will give a nice picture of what is going on here. Although it's pretty apparent from the energy levels, but it's a nice, I think it's a nice way to look at it. It's the way I personally think of it. So this here is frequency, and think of a spectroscopy experiment where you're probing at these frequency and looking at the response of the system. So the y-axis is going to be the response of the system. So essentially the density of states or the absorption spectra or whatever. And I'm going to do like this. And we'll assume that the atom is at a higher frequency than the cavity. Okay? So if we have no interaction, then, we will just have some omega q over here, and we will have some omega c over here. Okay? This will be omega q and omega c. This is with no interaction. But when we add the interaction, what happens is that these peaks start to split. Okay, so let's look at over here. I'm going to rewrite the Hamiltonian in a slightly different way. So what I'm going to write here is, so I'm going to look at this part now, and I'm going to write, we're going to have h bar omega q tilde sigma z, this is over 2, plus, all I'm doing is I'm rearranging the terms. So omega c tilde plus chi over 2 sigma z a dagger a. So I wrote the exact same Hamiltonian that's up here. I just rearranged the terms. And what you can see is that this Hamiltonian has, find this term of the qubit, and it has here this other term, which looks like h bar something a dagger a. So it's a harmonic oscillator whose frequency is omega c tilde, which is now shifted dependent upon the state of the qubit. So if the qubit, okay, I'm going to erase these two because they might confuse us a little bit. So I'm going to erase these two to avoid confusion. And I'm just going to write the two peaks over here. And then we have one peak, which we will call E, and another peak, which we will call G. Okay. You can see that the harmonic oscillator now has two frequencies. One frequency when the qubit is in the ground state, and another frequency when the qubit is in an excited state. Okay? This is due basically to the interaction of the atom with the qubit. So if you go and you ask the cavity, what frequency are you? What is your resonance frequency? Basically you send some probe signal at the right frequency. If you see a response there, you know the state of the qubit. Okay. On the other hand, we can rewrite the Hamiltonian in a different way, exactly the opposite way. So we can write it h bar omega c tilde a dagger a plus h bar, let me not get this right, over 2, there we go, omega q tilde plus chi a dagger a sigma z. Now what does this look like? Anyone? we're looking at the vicinity of the qubit frequency of omega q.
Shifted atom, shifted to lower sigma.
Exactly, an atom that is shifted, but it's shifted in a discrete way, right? A dagger A, what does it do? It counts the number of photons. So if we have 0 photons in the cavity, we're going to have a peak for the qubit. So this is a peak. The frequency, the transition frequency of the two-level system, if there are 0 photons in the cavity. But if there's 1 photon in the cavity, we're going to have another peak. And another peak. And another peak. And so on for all the photon numbers in the cavity. Now at this point, it's important to mention that this, what I'm showing you here is the spectra, and I put some kind of line width, a little bit of line width on these spectra peaks, because I assumed some decay rate. We're not talking about open quantum systems in this course. It's a little bit out of the scope, but cavities and also atoms, they have a natural lifetime. They decay. Okay, there's losses in the currents going around in the cavity. The atom can spontaneously decay also according to its density of states, the density of modes that it sees around. So there's going to be some natural line width. Okay? And what I've done here, the way I drew it, is such that the natural line width is basically very, very small. Okay? But this brings us to a discussion of the different regimes of the Jaynes-Cummings model, okay, which we haven't discussed. So that's what we're going to discuss now. You see, if the line width, if the decay rate of the atom or of the cavity is wider than this chi parameter, which is usually the case, then all this looks just like one big transition. Okay, so you can think of it as, something like that. If this is the line width of the atom, wide like that, then you can't see these peaks. But if you drive the cavity really hard, what's going to happen? You're going to see this line shape slightly shifting. Now, this effect of the line shape slightly shifting it's a manifestation of what is called the Stark shift. Okay, you apply a field, and you apply a driving field, and your atom is moving in response to that applied electric field. Okay. So that is that. Okay. So what I'm gonna, maybe I'll do it up here. So I'm gonna define basically two regimes for the Jaynes-Cummings model. The first regime, the usual regime is basically the line widths, which we'll call kappa. Kappa is usually the line width for a cavity, and gamma is usually marked as the line width for an atom, okay, or a two-level system. And the first regime, this is called the strong coupling regime. And the strong coupling regime mainly refers to the on-resonance Jaynes-Cummings model. It refers to it because it's when omega naught is basically much larger, or larger, it doesn't have to be much larger, larger than kappa and gamma. The decay of the cavity or the decay. In this regime, the splitting of the levels on resonance is distinct. Right? So if we're looking on resonance, we have these doublets, we can actually see the doublets being split. If we're not even in this regime, if omega naught is smaller than these, then all that is happening due to the Jaynes-Cummings interaction is that the line widths get broadened Even on resonance, they just get broadened and it just looks like a shorter lived atom. Okay, that's all that happens. We cannot see any manifestly quantum features. But as you get to large enough Rabi frequencies, and this is really the breakthrough of the cavity QED system that we're going to see next, and trapped ions and all those works that were done in the 90s, that's really the pioneering work that they showed. They went into the strong coupling regime where on resonance they saw the splitting. Okay? So you get split peaks on resonance. The other regime is when chi, our small parameter here, is larger than kappa and gamma. And this is sometimes referred to as the number split regime, or strong dispersive regime. And in this regime, what is happening is that you can actually see these distinct peaks. Okay? The frequency of the atom itself becomes now split according to the number of photons in the cavity. And this requires significantly larger interactions because you want omega naught squared over delta to be larger than the line widths of the atom and the thing. But you can actually reach these regimes in experiment. Okay, so what I want to pull up now is an experiment showing exactly this number split regime without discussing the system because it's in a superconducting qubit system. This experiment is from 2006, I think. We'll see. I'll pull up the paper and I'll do share screen. Can you see my screen? No, I did not do share screen. Share screen. Share screen. There we go. Okay. So, hang on. There we go. So the system that we're talking about, just so you understand, this experiment was done on a superconducting qubit. But before we do that, I want to show you this. So this is there. Okay. That. Okay. So what you're seeing here, the x-axis on this figure, this is basically mapping out kind of phase space of cavity QED or circuit QED regime. So a two-level system interacting with a mode. And on the x-axis you have delta. Gamma over here, this is the highest decay rate. So the faster out of the decay rate of the cavity or the atom. And on the x-axis you have delta, that's the detuning. And on the y-axis you have G. G is a very common way of representing the Rabi frequency. There's a factor of 2 between them. So 2G is omega naught. So in our notation we used omega naught for the vacuum Rabi frequency. A lot of the time you will see G come up and 2G just equals omega naught. Okay, so you can write that down for yourself. So, and what you can see here is that, so for very small detunings, you have the strong resonant regime, that's in purple, right over here. Right? In pink is the usual case. This is the dispersive weak. So you basically get kind of like these Stark shifts and so on. This is what happens for most systems. Okay, and you can see there are 4 distinct lines for just four systems: quantum dots, alkali atoms, and Rydberg atoms. Rydberg atoms are what we're going to talk about in cavity QED. And you can see that for natural atoms, the G's are relatively low, and it's kind of hard to go into the strong coupling regime, but you can. You can go into the strong coupling regime, and you can even see that Rydberg atoms can reach the dispersive strong regime, where you can just barely see the split peaks. Although I'm not sure if that was ever done in experiment. And deep into the dispersive strong regime, you can see here circuit QED. You can extend it even further because there's a lot of versatility there in terms of G. You can define G to be far, far larger than what is shown in this figure. But when you go deep into this regime, then you can actually see these number split peaks. And this is exactly what they did in this paper. So this paper, like I said, so this is 2007, not 2006. And what you can see here, so here what I'm showing you is basically spectroscopy. So basically, it's probing the qubit. It's probing the frequency of the qubit. And what is happening is you're scanning the frequency and you're probing the frequency of the qubit. I'm not going into the details of how that is being probed. When we do superconducting qubits, you will understand. I will talk a little bit about how to do spectroscopy. But what you can see here, so there is a coherent state being injected into the cavity. Okay, if you look at the, just so you understand the setup, it's a chip. This is the artificial atom over here, this little teethy thing. And it's coupled to the snake over here, and the snake is basically your harmonic oscillator. That's your electromagnetic mode. So you have atom cavity coupling. But what you want to picture in mind is the Jaynes-Cummings model. And here they inject a coherent state into the cavity. So you have a microwave. This is microwave frequency driving the cavity while the atom is being probed. Okay? And you can see these distinct peaks corresponding to the number state distribution of the coherent state. Okay? And below you can see this was done for a thermal state. So you have the cavity at a finite temperature, and you can see the distribution according to a thermal state. Okay? So this is, I think this is the first demonstration of number split peaks and this number split regime of the Jaynes-Cummings model. Okay, so what we're going to do now,
why the amplitude decays for large numbers?
Well, remember, this is if you look at the coherent state, remember the coherent state is a Poissonian distribution with a certain average. So the harder you drive, the center of this distribution is going to shift to higher numbers, and then you're going to have some distribution around these numbers. Okay? So as you go to higher numbers, there's less probability. Okay? This is a Poissonian distribution. Does that answer your question, or were you asking something else?
Yeah. So here the average was 1?
Yeah, here I'm guessing in the figure they're getting coherent with average of 3. You can see here. So here the average was 3. You can also see that towards higher and higher photon numbers, the spectra kind of gets messed up, but this is some other effect. So yeah. Okay, any other questions? Okay, if not, then we'll take a 10-minute break. Then we'll talk about the seminars and talk about the cavity QED systems and how these things come into play over there.